Hello everyone. As we get ready to look at JASP, I want to point out, and you'll be able to see this when you actually start looking at the application, but there's a series of tools under each of the categories that is classical, sort of classical, or sometimes called frequentist tools. And then underneath that, there's going to be a listing of the same tools, but in Bayesian version. And I wanted to explain this. We're probably going to stick mostly with the classical tools because for data mining, that's fine. Although I want to go through a couple of examples and give kind of a bit of an explanation of what Bayesian is, just so you know what it is, because you're going to be looking at it. It'd be useful for you to see what it is. So the classical approach to statistics, sometimes called frequentist, is where we go in and it's what we're normally accustomed to. So we will draw a sample, and that sample is supposed to represent a population. We will do, if you've seen the earlier videos, you'll do the hypothesis, null hypothesis, all that stuff, and we'll run a test on that sample to see if we can reject the null hypothesis and accept the hypothesis. So in many cases, that tells us the likelihood of something or the probability that something is going to happen or not going to happen. And then we can infer that result back to the population. And that's all in the earlier videos that I created. So that should be fairly clear and fairly solid. But what that does is it gives us a singular objective measure that we basically, we run through that process. We come up with the hypotheses, the null hypothesis, we test it, we either reject or fail to reject the null hypothesis, and it gives us a singular objective measure that is hopefully accurate or as accurate as possible that we can then apply back to the population. And that's classical statistics. Here's an example. So say we have a sample of 1,000. That could be 1,000 whatever, 1,000 anything, and just 1,000 measurements. And the mean of that sample is 15.5, and the standard deviation is 1.2. So given what we learned about statistics and standard deviation and the percentages of the population that live in each of the standard deviations, we then know that there's a 68.4% chance that each person is between 14.3 and 16.7, each person in our sample, because that's one standard deviation above and below the mean. We also know that there's about a 95% chance that each person is between 13.1 and 17.9, because it's two standard deviations above and below the mean. So those percentages can translate out to probabilities of 0.684 and 0.95 respectively. With Bayesian, and going back actually, that is what we call prior knowledge. So really and I'll make this point a little later in the video, but what Bayesian work does, what Bayesian methods do, is they allow us to make adjustments to prior knowledge. Classical statistics will give us that prior knowledge. We will know measures, we will know likelihoods, we will know probabilities because of the tools that we use in classical statistics that we're fairly familiar with or will become more familiar with throughout this class. What Bayesian allows us to do is to update that prior knowledge because we have new knowledge. So here is a little bit kind of an illustration using our previous slide information. Bayesian allows you to take your original measure or your prior knowledge of 0.684 and 0.95 and adjust the probabilities because we have new information or additional information. So in its simplest definition, Bayesian allows you to take the initial objective measure given by the classical frequentist methods and refine them with new information. And keep in mind the term prior knowledge, because prior knowledge is the same as the initial objective measures that classical gave us, but prior knowledge is the terminology or the nomenclature that is frequently used when defining what Bayesian methods are. So Bayesian can provide a more accurate prediction of probability depending on the situation and what is known. There are some things that are good for classical methods. I mean, many things are good for classical methods, but there's some things where classical methods will be sufficient. Bayesian won't add anything to it. In fact, it could detract from it. So we're dealing with examples where for example, we want to test out some metric about all Central Washington University students. So we're going to do a sample of 100 students that is representative of the population. And that's all the information that we have. And we're going to get information about that 100 students and then infer it back or apply it back to the population. That's fine. It's a fine use of classical statistics. But there are some tests that are actually better for Bayesian because we get additional information. And so the probability or the likelihood of events occurring can be modified when there is additional information that we can draw from. There's also at times when it's not convenient or possible even for us to do a representative sample. We might want to do some sort of a analysis of how well graduations go at Central Washington University. Well, technically there are only 3 a year. And for us to get a big enough sample for us to use traditional classical statistical methods, it's not possible. We'd have to wait 10 years, 20 years. And by then, so many of the factors would have changed that it wouldn't even be a fair comparison. So that would not be a great use of classical sort of, sample statistics where we were taking a sample and applying it back to the population. But we might be able to use Bayesian methods for something there. Here's an example. I'm going to go through a couple of examples. I'll first do the classical statistics part. So let's imagine a student named Sophia is a runner at her school. And we want to know what is the chance that she could run 100 meters in 13.5 seconds. Well, we have 200 runners. And so we measure the fastest that each of those 200 runners can run 100 meters. The mean speed is 15.5 seconds for 100 meters. And their standard deviation is 1.2 seconds. Okay. So using a method that I'm not going to go into here, because there's a definite method where you can measure a specific piece of space underneath a standard curve. But we can calculate that Sophia has a 4.8% chance of running 100 meters in 13.5 seconds or less, based on the fact that the mean for 200 students is 15.5 and the standard deviation is 1.2. So we know that that's pretty unlikely that she's going to be able to do that, but we know that it's a 4.8% chance. So we calculate the area under the curve that represents 13.5 and lower, and it's 4.8%. And that is our singular objective. It becomes our prior knowledge, right? It becomes the knowledge that we have. So it's really not prior to anything until we apply Bayesian methods, but it becomes the knowledge that we have. Sophia has a 4.8% chance of running 100 meters in 13.5 seconds or less, and that translates to a probability of, that's not supposed to say probability, not probably, of 0.048. So we're done. We have our answer, that it's going to be a 4.8% chance. But what if we knew these two things? So to be on her track team, anybody who wants to be on the track team has to be able to run 100 meters in under 14 seconds, and we know that Sophia is on the track team. Without going into the actual mechanics of it, I can let you know that we can apply Bayesian methods, and given that information, Sophia's probability of running 100 meters in 13.5 seconds or less still 0.048? No, it's not. It's now 0.45, or she has a 45% chance of running 100 meters in 13.5 seconds or less. Why? Because the Bayesian methods allow us to draw in additional information and modify our prior knowledge, modify our prior metrics. So we were able to include that Sophia is on the track team, and that to be on the track team, she runs 100 meters in under 14 seconds. So in classical, each time Sophia runs 100 meters, she's got a 4.8% chance of hitting 13.5 or less. We don't take into account the 14-second requirement that she has to hit in order to make the track team. But with that knowledge, we were able to make a more informed estimate using Bayesian methods. Here's another example. 10% of the people in the area have disease X. So you have a 1 in 10 chance of getting disease X, and your probability is 0.1. And that's a classical result. It becomes your prior measurement. But now here comes some new information. Say the doctor tells you that you have disease X, but the doctor tells you that the accuracy of the result for the test for disease X is only 8%. It's only 80% correct. So what does that mean? That you now have an 80% chance of actually having the disease? That could be one other bit of prior knowledge if we wanted to go ahead and just sort of apply direct classical stats, depending on how they came up with that 80%. But no, that's not actually how it works. Using Bayesian methods, we can combine the 10% and the 80%, and we can calculate that the chances of you actually having the disease, given your population in your region and the 80% inaccuracy rate, is only 31%, or a 0.31% probability of having disease X. So that's another example of the application of Bayesian methods to combine metrics, to take prior knowledge and adjust it or make it more accurate. And another example. Here's what we know. Tom has a 40% chance of losing his job in a recession. But if there's not a recession, then that chance drops to 5%. In any year, there's a 10% chance of a recession. And we know that Tom lost his job. So our question is, what is the chance that there was a recession the year Tom lost his job? Well, again, through a series of calculations that I'm not going to go into here, we can determine that when we combine all those metrics together, we can take the basic statistics that we got, the 40%, the 5%, and the 10%. We can take all those and we combine those all together, and we can determine that there is a 40% chance that there was a recession the year that Tom lost his job. And that's an example, by the way, of one that's not so great for classical statistics, but really great for Bayesian. So the bottom line, prior beliefs or prior information get updated with new data under Bayesian methods. And that's if we have new data. Classical gives us the prior knowledge, and Bayesian, if we have new data, Bayesian allows us to use that new data to update the prior belief with the new data. I've attached below and I'll put the slides for this presentation into the module so you'll be able to get to this link, but a video that I think does a really good job of showing you how you acquire prior beliefs with data, and then how you can go in and utilize additional data that is relevant to the problem to come up with a much better result, a much more well-informed result. Don't worry about the math. Don't worry about the the probability and all that. And also don't worry about the code. It's just Python code. Just kind of listen for the concepts to see how you as the pirate can do a better job of determining the likelihood of finding your treasure based on the additional information that your robot gets to you. So when to use classical or Bayesian? For much of the data mining we will do in JASP, we are going to stick to the classical methods, as I said. Those are also called frequentist methods. If there comes a time when it's useful for us to look at the Bayesian methods, then we can take a look at those. I just want you to know what Bayesian is, that it's taking, information, prior knowledge that we get from classical statistics, and allowing us to include additional information to come up with better predictions or better probabilities. So for many tests, Bayesian methods are not available, or they don't work for us, or they don't do for us what we want them to do. So that's why I'm going to stick with classical. And then there's this, and I just want to reiterate, while there's been a lot of statistics so far, this is a data mining class. It's not a stats class. And while there's quite a bit of overlap between those things, I want to emphasize from this point forward that this is really about finding good information in a data set. And I'm going to spend the rest of the class showing you how to do things of that nature.